Now, what I want to start doing today is to set the scene for the evolution of the human genes and the evolution of human culture. Now, I'm a biologist, basically, and I will tell this to you. I know that probably within some of you there are some people who have been taught and wish to believe that there was no evolution. Human development was literally as in the Bible and so forth. No problem. I wasn't there. I don't know how it happened. The only thing I can say is if it didn't happen as modern science and modern evolutionary science thinks it happened, with this incredible amount of consistent evidence and almost no inconsistent evidence, and if God is all-powerful, why did she go to so much effort to make it look like it happened a la Charles Darwin? That's a tough one for me to figure out. And to me, the evidence is overwhelming. You don't have to believe in evolution to do well in this class, but you have to understand the arguments. Your own personal belief is your own personal belief. It's kind of interesting, though, we find, once did a poll of how many freshmen believed in the literal Bible, and it was a surprisingly, to me, a high number, 25% or something like that. And when you poll our seniors, the number is a lot lower. So you make up your own mind, and I don't ask you to leave your faith behind at all. That's your business. Given the situation of the quite apparent evolution of our cells, which we will talk about, evolution and natural selection are always in response to the environment. So we have to understand the environment itself. Now, for me to understand the environment, as to understand anything else, we always have to start with questions of the energetics of the situation that we're dealing with. The energetics of everything that happens has an energy component. You can never fully understand anything without understanding the associated energetics. So, let's start with trying to understand the global environment, the sources of energy on Earth. Mostly we worry about radiant energy coming from the sun. Okay, what is radiant energy? We have three types of energy, of heat energy basically, or let's call it heat energy. We have radiant, that's energy that's more or less unassociated with matter. We call it the photon flux or photon flux density. We'll talk about that in a moment. It's something happens in the sun and the most extraordinary thing happens, packets of energy are sent to Earth. And it runs basically all life. There are other ways that heat can be transferred. This is radiant energy. It does not require matter. You can have conduction. If you're holding an iron rod and you make a fire at this end or apply heat with a blowtorch at this end, the molecular motion of this iron rod will be enhanced and will travel in this way so that after a while, if I put my hand here, I'll get scorched. That's conduction of heat by molecular motion. The third way is by convection. Convection is the movement of heat in the parcels of air mass. This energy is coming onto the Earth. There are other sources, moon, stars, etc. They're trivial. And there's energy that comes from the Earth's core, from radioactive decay deep in the Earth. That can be important in some cases, firing volcanoes and so forth. But principally we want to worry about the radiation energy coming in the relation of a tilted orbit to the Earth. And as it goes around, as it rotates around the Earth. So this energy that comes into the Earth hits the Earth, and the Earth is at an angle so that we have the seasons. So if this is Argentina, Southern Hemisphere, New Zealand, Australia, they're having summer now. And if that were emitting light in all directions, the tilted Earth would come around, and then we would have our spring and their fall, and then their winter and our summer. The reason is you get a greater photon flux density if you are tilted to be more nearly perpendicular to the sun's energy coming in. Now, this is the distribution of solar energy at different parts of the Earth by season: January, June, and December. Libreville on the equator has 2 peaks in solar intensity as the sun passes over twice a year. At the other extreme, Spitsbergen, northern Norway at 80 degrees, has no light at all this time of the year, January and February, and has a peak in the summer, as we have a peak. Now we're about 40 degrees, that's Lisbon. So we have a situation where the sunlight in the summer is about 2 or a little bit more times the intensity of what it is in the winter. So this gives you a perspective that all parts of the Earth get not exactly the same amount of sunlight, but the highest sunlight you get is in the furthest north. Where do you grow the biggest pumpkins in the United States? What state? Alaska. My wife is nuts about flowers. I like them fine. We were in Ushuaia. Who knows where Ushuaia is? Tierra del Fuego. Where's Tierra del Fuego? Tip of South America, okay? Down where Charles Darwin worked. We're following in his footsteps. The flowers that were there in January were unbelievable. Lupines this big, just each lupine this big. Why? Because they've got about 24 hours of sunlight. They can really cook for that few months of the year that they have lots of sun. So the amount of sun, if you integrate each of these over the year, integrate the area of sunlight each of them gets, you get quite a bit more over the equatorial areas than you do over the polar areas. And let's take a look, another way of drawing that, and let's look at what the consequences of that are. I'm going to drop back and talk about it this way for a moment. The most important component of understanding on the Earth's surface the photon flux density is the degree to which a square meter of the Earth's surface is perpendicular to or relatively oblique to the photon flux coming from the sun. So what this means is the most thermal energy, or most radiant energy, absorbed on the Earth's surface is at the equator, on the average over the year. Not because the equator is closer to the sun. The equator is, in fact, I guess, 4,000 or 5,000 miles closer to the sun, but out of 93 million, that's nothing. What's important is the angle which determines how much of the photon flux you intercept. as you go increasingly away from being parallel to the incoming radiation, each square meter absorbs less and less sunlight. I can even feel it here. I can feel the warmth from this lamp on my hand, just a little bit. And when I tilt my hand like that, the photon flux density has become sufficiently smaller so that I can't feel it anymore. You could do the same holding your hand up to the sun on a good, bright, sunny day. The Earth is basically a giant heat engine driven by energy coming in from the sun, which is denser at the Earth's at the equatorial regions. Now, what happens at the equator is that on the x-axis, the latitude from the equator to the North or South Pole. And here we have, I think I can do it this way. I got a new toy here. This is the incoming solar radiation, which is very high in the tropical areas and falls off sharply. This is the integrated radiation over the year with latitude. The outgoing terrestrial radiation that goes to space, which re-radiates to space as, you don't have to know this, but the fourth power of the temperature. It's affected mostly by the temperature, which isn't very different from the equator to the North Pole. The output looks something like this. Here we have a surplus of energy coming into the Earth. Here we have a surplus of energy being released to outer space. That's where it all goes. It goes to outer space. So, in this situation, here's a thought process for the more mathematically inclined. I'm going to tell you that the integral of this area is the same as the integral of this area. Doesn't look that way, does it? There's a trick. Who can figure it out? I'm not going to give you the answer today. Okay, here's my toy Earth. Bought it at a sort of a Discovery Channel type store. And we're just looking at the solar radiation. I'm tilting it a bit because the angle's coming up from there. You get a large absorbance of net absorbance of energy here. Very little absorbance here. And of course in winter, down here in the South Pole, tilted away, it's like that. The summer, this is our summer, this is Argentina's summer. Okay, now, the Earth is in approximate temperature equilibrium. How does the heat, the excess heat, from this part of the world get transferred to this part of the world? Okay, you've already done a little bit of reading. Who's got an answer for this? Is it in the reading? Who's got an answer in here? Yes, sir. Say your first name, please.
Stephen.
Steve.
Through ocean currents and air currents.
Ocean currents and air currents. Okay, through the motion of fluids. What are fluids?
Well, they're, I guess you mean
Fluids are
matter that can move.
matter that
Can move.
takes the shape of its container.
That can move wherever it wants, or
No, not wherever it wants, wherever it's pushed by energy.
yeah.
All right, it has no volition. So, matter can move that way. So, the fluid dynamics, meaning the motion of fluids on the surface of the Earth, is such that heat is transferred from the equatorial regions north and south.
Is that convection?
By convection. That is the movement of heat in masses of air and water. Now, the principal way is something like this. The solar energy hitting the Earth's surface heats the vegetation, and the water heats the Earth's surface. That energy is transferred to parcels of air which rise. And they move north or south, go the other way too. And the return flow is essentially on the Earth's surface. So it is the energy of the sun heating the Earth at the Earth's surface that causes the fluids of the Earth to distribute the heat. About 80 to 90% of it goes in the atmosphere. The heat is transferred in the atmosphere. The rest goes in water. Steve, do you have a famous example of a water system moving heat to the north?
The Gulf Stream.
Gulf Stream, okay? And there are many of them around the Earth. And if you should be interested in fisheries and so forth, you'd learn a lot about them while you were here. Okay, so that's how the Earth's basic heat engine works. Now the second, it's more complicated than that though. And it goes something like this. The heat rises here at the equator. It goes up to a height of some 5 miles or so, a little more. And then it goes north and south because high pressure builds up in the upper atmosphere over the equator, because all these air masses are coming into that part of the atmosphere, causing high pressure, pushing the air masses north and south. Now, when those air masses, remember at 5 or 7 miles in the Earth's atmosphere, reach about 30 degrees north and south, they descend. They have cooled enough so they don't have enough energy to stay in the atmosphere. At that point, they fall to the Earth, and because there's low pressure at the equator, because air masses have been removed by them moving upward, these wind patterns go towards the equator. These are called Hadley cells, after the early English meteorologist, I believe it was John Hadley, whoever Hadley. And this information was extraordinarily important to the English and to the Portuguese, who really were the first people to figure it out, at least in Europe. There were many Arab traders that figured this out long before, as well as many Chinese who had figured it out long before, but the records are not as clear. Why was it important to the English to know what these patterns were? Sailing ships. And what does the sailor want to know? Where's the wind going to blow? Where's it going to blow tomorrow? How much is it going to blow? All those things were very important. Okay, now I'm going to tell you it's a little bit more complicated. The next step of complicatedness is the friction of this cell drives a second cell, both in the northern hemisphere and the southern hemisphere. And maybe there's a third cell further up. That's a bit of a simplification. Any real meteorologist would have my neck, but we're trying to get you started on thinking about things this way. Okay, now something funny happens here in this process. The winds are shifted. Why are the winds shifted? Anybody know?
Coriolis.
Coriolis effect. The story is that when they first invented long-range guns and shot at targets miles away, the shells would fall to the right of where they were pointed. Now, some people say that story is apocryphal, which means of doubtful origin. But it's a good story, so I'll tell it to you. The Coriolis effect says that any motion in the northern hemisphere will be, the particle in motion will be shifted to the right. For example, icebergs drift at 45 degrees to the wind, 45 degrees to the right, in the northern hemisphere. The toilets supposedly, I keep meaning to check this and I never have. The toilets supposedly go around to the right in the northern hemisphere and the southern left in the southern hemisphere. So anybody going to the southern hemisphere, please do the toilet test for me, please. We know it happens for all kinds of things, and most important, it happens for the fluids, masses of air. So the movement of the air is shifted to the right in the northern hemisphere. So the wind is basically being pushed in this direction, but the Coriolis effect pushes it, shifts it this way. Why? Because the Earth is also rotating from west to east. It's spinning in this direction. If you're standing on the equator, you are really booking. You got to do 25,000 miles in 24 hours. On the poles, you're just doing this, right? How many miles do you go in a day? 0. In between. And these are the most consistent winds on the face of the earth. They're called the trade winds. Why do you think they're called the trade winds? Any idea?
They were used for trade.
Used for trade when they had sailing boats, right? So people were very interested in doing the trade and various things, including very bad things. This trade was determined by the winds, and if you were a good sailor, you would understand this very well. And they're very steady. So, for example, I do a lot of work in Puerto Rico, and it's always a comfortable place to be there because the trade winds are always blowing. It's a little bit hot for me in the summer, but you always have a nice cooling breeze because you're sitting right there in the trade winds, and they come in from the east, and they bring a lot of moisture to, for example, the Luquillo Mountains where I work, and that's why there's a rainforest there. We'll talk some more about that in just a minute. Now, the Coriolis effect in an analogous situation shifts the winds to the right, this wind that's going like this, and provides us with westerlies. Where does our weather come from? From the west, right. And you want to know what the weather's coming in, you know, if the storm's coming in to hammer you, just look to the west. There it comes. Okay, so that's the reason for our basic patterns. Now, what happens when these weather patterns intersect the land? Okay, well, here's an example, and again, let me tell you, we were just experiencing this to the nth degree. Because we were up on the top of Pico del Oeste in Puerto Rico at the top of the mountain. And we were there for about 10 days, not always at the top of the mountain. And I got soaked day after day after day. And we're having to deal with moving all of our heavy equipment around, sliding down the slope and all that kind of stuff. So, I mean, it's a very, very real thing. These are not things that are just kind of arbitrary. So what happens is when the wind air masses come in and are moved up any land effect, you cool the air. Cool air has less energy. If it has less energy, it can hold less water in suspension. First you get clouds, and then you get rain. So it tends to rain on the windward side of mountains. Then when the cloud goes down on the other side, you get a rain shadow on the other side. This is called the orographic effect. The word O-R-O-G refers to mountains and so forth. Okay. Now, what do these things mean to our Earth, to the ecosystems of the Earth, and to our own history, or prehistory? The answer is everything. Where are the rainforests of the world? Well, here, in the middle of Africa, here, in the middle of South America, all over the place, in tropical Asia. What's going on? Well, what's happening is that the ascending air masses here going up at the equator, because the sun input is most intense there, the rising air masses cool. The same way as on the mountain. They cool. They cool, they hold less water, the water falls down, and then more water, more air masses come up, and the water keeps going down, the air masses keep going up. They cool, and eventually it rains on the equator, and this is where you get the most rain on the surface of the Earth. For one thing, warmer air masses can hold more water. Second, if they're cooled, they release more water. And so what you get, there are tropical forests, tropical rainforests, basically are found only on the equator or near the equator. Not all tropical forests are rainforests. There are many, in fact, there's a larger area of tropical dry forest. But the tropical rainforests are found in the vicinity of the equator. They're also found, Puerto Rico, for example, is about 20 degrees north of the equator, but it gets a lot of water there because the winds have been going over the ocean. Water enters the atmosphere over the ocean. And so you get a lot of water coming into the atmosphere from the ocean, which is, the converse is also true. And we'll get to it when we talk about deserts. Basically, water enters the atmosphere over the oceans, especially over warm oceans. Much of the rain that falls on United States agriculture that feeds us all in the Midwest last saw the surface of the Earth in the vicinity of Borneo, over here in Asian Pacific. And therefore, deforestation in tropical forests, such as on Borneo, affects American agriculture in various ways. The whole world is linked by these Hadley cells. Our fate is linked by what goes on in tropical forests to some degree. As you go away from the equator, it gets a little bit more seasonal, because when does it rain in the tropics? It rains when the sun is overhead. That's it, basically. So when is the sun overhead? The sun is overhead, well, depends where you are. The northern hemisphere in the relative summer months, and the southern hemisphere in our winter months. Who knows what the tropics are? What does the tropics mean? Okay, where the sun is directly overhead at least 1 hour of the year. That's from 22.5 north to 22.5 south. That's the tropics. And there are lines that are called the Tropic of Cancer and Tropic of Capricorn, in famous books by that name. And that defines the limits of the tropics. So when you're near the Tropic of Cancer, the Tropic of Capricorn, you don't have rainforest, you have tropical seasonal forests. And we'll take a look at what some of those look like next time. Now, What happens when air masses descend at 30 degrees north and 30 degrees south? If air masses cool on the equator when they're rising, what do they do when they're descending at 30 degrees north and south? They warm. Good. And when they warm, what can they do? What do they have when they're warmer?
More water.
More energy. More energy. You have more energy, your molecules are moving faster, you can keep the molecules of water in suspension better. So the air can hold more water. Those air masses come down and hit the land surface, and what do? Just suck the water right out of it. And you have a desert. All right? So, if you look at a map of the world with colors appropriate to the ecosystems that are found there, you find an area of deserts at about 30 degrees north and south. Arizona, southern Arizona, parts of Mexico, Kalahari Desert in Africa, 30 degrees south, and the biggie, the Sahara Desert, 30 degrees north. All right? Now, we also have enormous deserts, Gobi Desert and others, in Asia that are not exactly 30 degrees north and south. We also have rather dry areas in Nevada and so forth, part of the United States, that are more like 40 degrees than 30 degrees. Why should that be? That's because these are areas that are far from the oceans. Remember, the oceans are the source of the water that comes onto the Earth's surface. And you get big deserts simply because they're very far from any source of water. Now, what's the story about Syracuse? Syracuse is, especially in the winter, pretty cloudy. Got a moderate amount of rain. Go up to Tug Hill, you get a whole lot of rain and snow. How come? Yes?
Just lake effect.
Lake effect.
Yes.
Same thing on a smaller scale. Air masses are traveling over Lake Ontario. They pick up. That's what happened to Buffalo. Well, who's from Buffalo? Hey, oh, look at all the Buffalonians. Hey, you guys like snow this year, huh? Now, why maybe this year in particular, I don't know, I just have a theory, is that the air mass, the lake was warm, right? This is a very warm fall. So the lake was warm and had a lot of energy pushing those molecules, it's called evaporation, out into the atmosphere. And the wind patterns were such that it hit you guys instead of Syracuse. We had 1 inch when you guys were drowning. How many feet of snow did you get? 7? A lot of snow. Okay, so that's a basic idea. Now, something that's obviously this pattern is a little more complicated around the world. You start getting wetter type ecosystems north of 30 degrees. Mountains can make a huge effect. How many have been to Washington State? What's Washington State like basically except for Seattle?
Dry.
Dry, it's a desert, right? Now what you are is that you're in the rain shadow. When the air masses, same deal, so air masses descend on the east side of the Cascades, then they get warmer, they can hold more moisture, they suck the moisture out of there, and it gets very dry, and that's where a lot of apples are grown and so forth, all right? All right, now let's take a look then of how this plays out on the Earth's surface with respect to vegetation. Beginning of our attempt to understand how the vegetation works. Incidentally, can anybody tell me why the most conservative political countries, England, the United States, Russia, and so forth, are found where they are, and why there's so many revolutions in South America and Africa and so forth?
They don't span.
It's the Coriolis effect. Any political action in the northern hemisphere gets moved to the right. Any political action in the southern hemisphere gets moved to the left. So that's why you live in such a conservative country, according to some. I hope you understand that's a joke. It's a good joke, though. It's a good joke. Okay, so let's go back to something resembling science here. The Coriolis effect is bringing in the air masses in a curve like this. Oops, I'm sorry, here's the equator. It's coming in like this and like this. Now, of course, the best example is the Amazon. And the mouth of the Amazon is almost on the equator. So these air masses are slamming into Brazil, into the Amazon basin, and they get pushed across the Amazon until they hit the Andes. And they hit the Andes and they're pushed up the slope. So it's wet the whole way. And let me tell you, it's wet. So this creates a massive area in the Amazon basin where most of the remaining tropical rainforests are even today, although that's changing rapidly. The same is true to a lesser extent from Africa. I have to tell you, I don't fully understand why it isn't wetter on West Africa and why the Congo is as wet as it is. So maybe one of you can tell me why that is. But I've never seen it explained well. So we have equatorial rainforests here. And as you go a little bit further north and south, you get deciduous forests. Deciduous means the leaves are dropped. The leaves are dropped not because it's too cold, but because it's too dry. So in southern Mexico now, in Chiapas, those areas, the leaves are being dropped. The trees are bare, even though the temperature doesn't get even to freezing, or even anywhere near it. Now, a little further north, and you tend to get a savanna. A savanna is a grassland with trees. But at 30 degrees north and south, except right on the coast, you get desert. Now, you go a little further north in the United States, in the massive interior of the United States, and you get steppe. All these words that are new to you, like steppe and some others I'll give you, are from the Russian, from the Slavic languages, because these were the guys, early ecologists, who figured it out the best. And this is simply grassland. And you get a little further and you get boreal, another Slavic word. Coniferous, you know, you go up into Canada, it gets all, or the top of the Adirondacks, it's all coniferous. And then further north, tundra, and even further north is ice. So these are the main ecosystem types in the world. Now we're going to be talking for a while, please write this down, about the ecological theater and the evolutionary play. The theater where it's taking place is ecological, is environmental. The play that's unfolding is evolution. Evolution both physically and biologically and culturally. And that's what this course is about.